Para mim não está aparecendo aqui no YouTube ainda. Agora foi. Okay, so bom dia and good morning, everyone. So today we start again. I mean, you have another talk for Brazilian Society talks on quantum optics, quantum information and related subjects. And today we have the pleasure to have Ángela Capel from the University of Tübingen here, that she's going to talk about her latest work related with the generic quantum Wielandt inequality for matrix and algebras, which is also related to thermalization of systems, which are a very interesting problem. So I would like to thank Ángela for having taken time to talk to us and talk a little bit about her work. Thank you, Ángela.
Okay, so thank you very much for the introduction. And well, of course, I want to thank the organizers of the Quantum Optics and Information Talks for inviting me to speak here today. I'm very happy to share with you some piece of my recent work about this topic that was already mentioned. So I'm going to talk today about a generic version of quantum valence inequality that is going to hold for both matrix and Lie algebras. And with this, I in particular will talk about the length of a matrix algebra, the length of a Lie algebra, and how we can apply some estimations of these quantities to various applications in quantum information theory. So I'm going to essentially talk about two different papers that have the references that I mentioned here on arXiv. So this is the first one with Yif and Jia, which is already on arXiv since January. And this one hasn't appeared yet, but it will appear during May. And this is in collaboration with both Yif and Jia and Yidong Shin. Okay, so let me start directly presenting the problem that I'm going to be discussing here, because actually the problem has a very simple formulation. And it's very interesting because it's a problem that already proceeds from this field of linear algebra. So it's something that is in principle completely unrelated to quantum information theory, but surprisingly enough, it has very strong applications in our field. So just to state the problem as it appeared around 40 years ago, the idea essentially is that we consider two n-dimensional complex matrices A and B, and now we consider just the generating system formed by both of them, so just the system formed by both of them. And we have the question whether words constructed with these two matrices can generate the whole matrix algebra or not. So what we are going to do essentially is take these two matrices as letters, and we are going to construct words with them. So just considering products of different orders of these matrices as letters, like something like this, for example. And we are going to consider all the words that we can construct from A and B that have length at most a certain natural number L. So we are going to consider something like this. So first of all, taking A, B, A squared, AB, BA, B squared, and so on and so forth, until we reach all the words that have length L. So something that I'm listing here. And the question is the following. What is the minimum length that we have to consider, so the minimum L that we have to consider, such that all words that we are creating on A and B of length at most this specific length span the whole matrix algebra. So essentially, if we are guaranteed that the system we were given, A and B, is a generating system, what is the minimum length we have to consider such that all these words span the whole matrix algebra? And as I said, this problem goes back to many years ago, to 1987, to the field of linear algebra, where Paz conjectured that for any generating pair S, like this one, he conjectured that the length should be of order n, where n is the dimension, well, it's all these matrices are n times n. So this is where n comes from. And this is the conjecture, and surprisingly enough, so many years after the conjecture, we don't have a general result that gives us a solution to this conjecture. But what we have is a best bound for any generating pair that is given by order of n log of n, so it has a log of n overhead, and this is from 2019. And the bounded path conjecture itself, which is 2n minus 2 specifically, is proven in some particular cases. So first of all, until dimension 6, it's doing just by explicitly computing all the possible words. And then for matrices that have distinct eigenvalues, for matrices, well, for pairs in which one of the two matrices is a rank 1 matrix, or one of them is a non-derogatory matrix, etc. So this is the statement of the linear algebra problem. And this is the first problem that I want to mention here, but we are not going to work directly on this problem. We are going to work on something that is very related to this problem, which is the following. So now we consider the same setting. We also consider two matrices that are two n-dimensional complex matrices, and again, the generating pair formed by both of them. And again, we want to generate the matrix algebra by spanning words on these two letters, but now we only consider the words that have the same length. So now we fix a certain natural number L. We consider all the words that have length exactly that natural number, so something like what I'm writing here. And of course, we have again the same question, which is what is the minimum length? So what is the minimum natural number such that all words on A and B exactly have of length exactly L, span the whole matrix algebra. So what is the minimum L such that this happens? Where now I'm writing here this equals L to emphasize that all the words have exactly the same length. And this is a problem that some people started to explore more recently, only in 2010. And now this is from the quantum information community. So in this paper from Sanz et al. From 2010, they conjecture that for any generating pair for which you are given the certainty that this is a generating pair, so this is going to generate the whole matrix algebra, they conjecture that the length should be of order n squared, where again, n is the quantity that is given as the dimension of the matrix. And again, as it happened for the result that I mentioned before, for the problem that I mentioned before, this is not proven in general. And the best proven result up to date is that for any generating pair S, what we can always show is that the length should be of order n squared log of n. So again, a log of n overhead. This was also proven in 2019, so very recently, 4 years ago. And same thing as before, the conjecture is proven in some particular cases. So in particular, in the same paper in which they stated the conjecture, they provided some examples for which precisely this optimal bound is satisfied. Okay, so until now, I presented two different problems. First of all, I presented the conjecture that for any generating pair, the minimum length L that we have to consider such that the span of S less than or equal L coincides with the whole matrix algebra should be L order of order n. And I also presented the quantum Wielandt inequality, which was, as I said, conjectured by Sanz et al. And this conjecture said that precisely in the same setting, but not considering all the words with the same length, the L that you have to consider here such that this is satisfied should be of order n squared. So you see that there's a difference between this order of n to this order of n squared. And these conjectures are actually pretty strong because they are asking for something that should happen for any generating pair. But now in the problems in which I'm interested more recently, they have to do with sampling. So that means essentially that if I want to sample certain matrices and I want to construct the words that are generated with these matrices, in principle, what I'm going to find is something that happens with probability 1, but it's not something that happens always. So that means that I'm interested in the question, what happens in these two problems only with probability 1? So essentially, almost always, but not always. And this is the main result that I want to mention right now, which is a generic version of quantum Wielandt inequality. And in this result, what we proved with Yifan last year is that with probability 1, both lengths can be taken to be of order log of n. both the length associated to pass and the length associated to Wielandt. So in these two cases, with probability 1, we can take here order of log of n and also here, and we would be fine. We would be spanning the whole matrix algebra. And this is the main result that I want to present in the first part of the talk. So what I'm going to do now is formulate it in a bit more formal way. And then I will present very briefly a sketch for the proof, because it's something that I think could be very interesting for some other problems as well. So I just want to give you an overview about that. And for that, what we are going to do is the following. So first of all, we are going to define something that is a V-generating system and the V length of matrix algebra. So what we are going to do is, again, consider Mn of C, so this matrix algebra, and we are going to consider a subset there. Now we don't need to have two elements as before, like here. We can have a bigger number of elements as long as it's a finite number. And what we are going to do is assume that this is a generating set, in the sense that we have to assume that there is a large enough L, such that if we take all the products of length L of elements that belong to S, then we are spanning the whole matrix algebra. Then in this case, we say that S is a V-generating system because it's generating the whole matrix algebra with Wielandt products, in the sense that all the products have the same length. And its V length is something that we are defining here, and it's just the minimum capital L, such that the products of length L of all these elements in S span the whole matrix algebra. And once we have introduced this concept, we can rewrite the result I was mentioning before in this way. So essentially saying that the Wielandt length of this generating system S is of order theta of log of n for almost all V-generating systems. So essentially with probability 1, if we just take a generating system, with probability 1, we have that the Wielandt length of such generating system is of order theta of log of n. And that means two things. That means that it's of order O of log of n, as I said before, and it also means that this is optimal. This is why we have a theta there. And the reason why it's optimal, I will mention why that happens now. But first of all, let me just give, as I said, some overview on the proof, because it's very simple to explain it just with a picture, and it can be useful for some other problems as well. So what we are going to do, first of all, for simplicity, is just assume that, again, S has only two elements, because, well, if it has a bigger number of elements, one can just generalize the proof to that particular case, but the idea behind it is exactly the same. So let's just do this for simplicity. And now we are going to have several steps that I'm drawing here, with the arrows going from one to the next one. And I will explain each of them now separately, but you will see that all of them are quite simple. So the first thing that we are going to do is consider n square words of length little l in A and B. And so that means essentially that we are going to consider products of this form, where A and B can be chosen in each of the entries of the word. And the length of the word is always going to be little l. And I haven't said anything about little l for the moment. What we are going to do now is determine how little l scales, essentially. But, sorry, the first thing that we are going to do is consider n square words. And what we will prove during this proof is essentially that these n square words with probability 1 will be linearly independent. The first thing that we can say about little l is that it is of order omega of log of n. And that's very easy to see. This is essentially by some counting argument. So essentially the idea is the following. If we are considering that L, sorry, if we are considering that we are constructing with words of length L n square different words, take into account that for each of these words, we can choose here an A or a B, here another A of a B or a B, here the same, and so on and so forth, which means that the total amount of possible words we can construct here is essentially 2 times 2 times 2, and so on, which means that in total we will have 2 to the power L different words that we can construct in this form. And since we need at least n square words in order to be able to generate the whole matrix algebra because of the dimension that Mn of C has, then this means in particular that 2 to the L has to be larger than or equal to n squared. And then it's a very easy computation to see that that means that L has to be of order omega log of n. So it cannot be smaller than this quantity. It has to be at least of order log of n. And as I said, this is just because you need to generate n squared words that are linearly independent. That's the only reason behind this. So this is like the easy argument to prove the lower bound. And now to prove the upper bound for L, this is slightly more complicated. And to prove the upper bound, what we essentially do is the following. So first of all, we consider any word. Like here, for example, we consider the word A, B, B, A. And what we do is essentially just write this in binary form. So here I will write it like 0, 1, 1, 0, which if we identify with the decimal expression, it would be just number 6. And that means that this word is the 6th word among all the words that we can generate here. So what we are doing is just creating some order. And now once we have established this order, what we do in particular is write a explicit expression for this matrix as the one that I'm drawing here. So now we have a matrix that has dimension n times n, and it has all these coefficients. And all these coefficients are going to be little polynomials on the coefficients of A and B, because they are going to be given by different products of the coefficients of A and B. But for the moment, this is just one step in which what we are doing is just rewriting this word in a different way. Now, once we have all these words, what we have to do is put all of them together. And the way to put all of them together is just by linearizing them. So here we have, as I said, one matrix that was of dimension n times m. And that means in particular that all the elements that appear in this matrix are in total n squared elements. So what we can do is write these matrices as vectors of dimension n squared, so 1 times n squared. And we can write them in columns of another matrix. So this other matrix is something that we call W. And this W, since we had n squared different words as an assumption at the beginning, that means that we put all these n squared in n squared words as columns of this matrix, and therefore W is a matrix that is n squared times n squared dimension. And now remember, what we are trying to do is prove that these n squared words are linearly independent, and that's something that we can achieve if we prove that the determinant of this matrix is non-zero. So the only thing that we have to do now is show that the determinant of this matrix is non-zero. And then if this happens, then we will have that all the columns are linearly independent. And if that's the case, then we will be done. So we will finish the proof of the theorem. But to explore this, let me give a little bit more of detail. What we are going to do is analyze each of the coefficients of W separately, and then see how these coefficients appear when we compute the determinant. And essentially what is happening here is the following. All the words that we wrote at the beginning were words of this form. So A can be written with all its coefficients as the expression that I write here. So A11 to A1n, and then here to AN1 and to ANN, and the same thing for B. So that means essentially that all the x that appeared here, as I said, were polynomials in these coefficients. And that means more in particular that now if we take the determinant of this W matrix, what we have is essentially a sum of -1 and plus 1, and different products of different coefficients of the A's and the B's. So that means essentially that we can write the determinant of W as an expression like the one I write here. So as I said, is either +1 or -1, depending on the position and depending on many different factors of, well, each different coefficient AI or BJ that appears here. And now each of these terms is a certain product of a certain amount of AIs and a certain amount of BJs. And that means essentially that you can write this whole expression as a polynomial as a big polynomial in all the coefficients of A and all the coefficients of B. And now we have to see that the determinant of this matrix is non-zero when we evaluate this polynomial in the specific values of the coefficients of these matrices. And that means essentially that we have to see that this polynomial is not identically zero. Because if this polynomial is not identically zero, then it means that the set of zeros of the polynomial has measure zero. And therefore, if it has measure zero, then that means that the amount of possibilities for the A's and B's that we can write in this procedure so that the output is a determinant that is non-zero is almost all of them. So it's something that happens almost surely because the complement has measure zero. So this is essentially how we conclude the proof. What we do is find n square words for which this polynomial has measure zero. And actually, if you want to have a little bit more detail of how this is done, it's because there is a way to prove here that one of the terms that appears in this huge sum of different terms only appears once. And that means essentially, if it only appears once, it already provides a polynomial that is not identically zero, because it would be identically zero if all the terms here appeared at least twice, one with a +1 and another time with a -1, and they annihilated themselves. But since this is not the case, since one term appears only once, this is how we can conclude that this polynomial is not identically zero. And that means essentially, as I'm writing here, that the zeros have null Lebesgue measure, and therefore the set of words that we consider at the beginning spans the whole matrix algebra almost surely. So the only thing that is left to be done is to show that these n squareds actually exist. And this is something that we didn't have to do because it was the most technical part of the proof, but it was done before in this paper of 2016, where Kleb and Spenko proved that there are n squareds of length, exactly the length I was looking for, so something that is of order log of n, such that this polynomial that is being created here is not identically zero polynomial. Okay, so this is how we conclude the proof of this result. And of course, here I didn't give the details, like the specific details how to do it, but I at least wanted to give you some intuition how this is done, because it's some sort of standard proof as far as I know that has been used for some other results. And for the moment, you could say, okay, you have shown here a result that has to do with linear algebra, but in principle, we are not seeing the connection to quantum information. And this is why now I want to show a couple of applications that directly appear from this result in, that directly apply this result in different contexts in quantum information theory. And the first one of them has to do with the cross rank of certain quantum channels. And for that, what we are going to do is, first of all, recall what I mean by this. So we are going to consider a quantum channel that is just a completely positive and trace-preserving linear map. So just a map that goes from the bounded linear operators in a Hilbert space to the bounded linear operators in another Hilbert space that is completely positive and trace-preserving, as well as linear. And we are going to assume that our quantum channel is further primitive. And a quantum channel is primitive if there is an integer little l, I'm calling it, such that for any positive semi-definite matrix rho, when we apply the channel L times, and then we compose it L times, and we apply it to rho, then the output is positive definite. So that means essentially that EL of rho is larger than 0 for every positive semi-definite matrix. When this happens, then the channel is said to be primitive. And the minimum L for which this happens is called the index of primitivity of the channel, and it's something that I'm denoting here by Q of epsilon, well, Q of E, sorry. And we can relate this actually to something that is the cross rank of the channel. And by that, to do that, we have to use the Choi-Jamil-Minkowski isomorphism. And the idea to do this is essentially that now, if we consider the channel and tensorize it with identity and apply it to this maximal entangled state constructed like this. Then, well, this is the Choi-Jamilkowski isomorphism, right? So this is how we can relate the channel to a certain matrix, to the Choi matrix. And once we have the Choi matrix, the rank of such matrix is called the Krauss rank of the channel. And in the paper that I mentioned before, from the quantum information theory community, they showed that the permittivity of a quantum channel is equivalent to having eventually full Krauss rank, which means that, well, as I said, after many different applications of the channel, at some point, this n-fold composition or whatever has full Krauss rank. So the rank of this W of e to the n power would be full, so it would be a complete rank. And apart from that, what they also showed is that the Krauss rank of a channel in general is lower bounded by this index of permittivity that I was defining here. So essentially, if we take a look now at the explicit definition of what I was... Sorry? Yeah.
It's looking here. Can you see me? No, you cannot see me.
No, I cannot see you.
Yeah,
now
you can see me, me and my group here.
Great.
Can you please give us a physical intuition behind this property, the permittivity, I mean?
A what, sorry?
A physical intuition behind this property. I mean, mathematically it's okay, it's well defined in your last slide, but physically, what does this mean?
So what this means is
interpretation of this thing.
I mean, it's a very good question. So mathematically, as you were saying, essentially what this means is that your quantum channel only has one eigenvalue of modulus 1, which is precisely the 1, no? So that's essentially it.
I'm thinking about things like the Frobenius theorem and things like this. I mean, that depends on the eigenvalues of the stochastic matrices.
Sorry, it's a bit difficult to hear you for some reason.
Okay. I'm thinking about theorems like Frobenius and things like these. That depends on the eigenvalue of the matrix, of the stochastic matrices and things like this. So is there an interpretation of this property like this one? I mean, physically sound?
It's a very good question. Yes, I'm not 100% sure what that would mean in terms of what you're mentioning here. But yeah, of course, for me, the most clear intuition is what we are saying here, no? That when you apply the channel enough times, you are removing completely the zero eigenvalues. So from the matrix. But I wouldn't know how to give you like what this physically means. How to give you an intuition about this.
No, actually, yeah, I still don't understand physically this thing. I'm trying to think about thermalization in process like this that depends on the eigenvalues of things.
No, about thermalization is much easier to see. I mean, when you consider this n-fold composition as just applying a certain channel of noise, for example, many times, what you're essentially saying here, it's equivalent to saying that your noise only has one fixed point. And that means essentially that this is always going to thermalize to this fixed point.
Thermalize to this, yeah.
Exactly. So about thermalization, if you want to see this channel as some depolarizing channel, for example, this is what it would mean. That there's always going to be thermalization to this fixed point of this noise evolution or whatever.
Okay.
So it would be something like that.
Okay, thank you. Thank you very much.
Okay, thanks. Yeah, so essentially I was talking about this permittivity, this property of permittivity for the channel. Just because if you take a look at what it means for the channel to have a full Krauss rank, it wouldn't be so difficult to see that this is equivalent to just having well, the notion of full Krauss rank is equivalent to just the notion of B-generating system for the Krauss operator of the channel. And this is just because if we consider a channel E that has Krauss operators like the ones that I'm drawing here, that means that we can decompose the channel with this expression. And therefore, having full Krauss rank would be equivalent to just having the fact that if we span all the products of all possible Krauss operators, this would span the whole matrix algebra for a minimal L, which would be the Krauss rank of the channel. So that means essentially that the result I was mentioning before can be interpreted here as the following consequence, which is that if we consider now a quantum channel that is generic, so again with probability 1, and this quantum channel has cross operators given by this collection that I write here, then the cross rank of these quantum channels, the cross rank of this quantum channel, and thus the index of primitivity of the quantum channel, it would be of order theta of log of n. Okay, so this is how you can relate this problem that in principle didn't have anything to do with from the linear algebra field to this application from quantum information. So again, the conjecture here is that for any quantum channel that is primitive, the index of primitivity of the quantum channel is of order n squared. And what we can see is that with probability 1, you can reduce that to log of n, and you are still fine. And this is the first application I wanted to show. And the second application also has to do with quantum information, but in a different direction. So now for matrix product states. And for matrix product states, let me just recall the definition very briefly. The idea is that if we consider a pure quantum state that lives now in this space, and by this I essentially mean that we are modeling L different sites that I'm drawing here as some squares, and each of these sites belongs to a G-dimensional Hilbert space, then we can construct a translation invariant pure state, like this expression here, where this is going to be just a matrix product state with periodic boundary conditions. So this is why I'm drawing it here as a ring. So I'm just tracing this part here. And this is why I can write this expression, where this ket element is just the product of all the legs that you can see here. And now for any different natural number L, what we can do is consider this map that is given by this expression that I draw here. So essentially the same expression that I was writing above, but now introducing the operator X in this part inside the trace. And there's a theorem from 2006 from David Pérez García and collaborators, in which they proved that this map is injective if and only if the span of all the products of all the possible elements that appear in this expression spans the whole matrix algebra, or in the notation that I was using before when I was describing all these things that had to do with the Wielandt problem. What would be equivalent would be to say that the Wielandt length of this set of generators is upper bounded by this capital L. And that means essentially that now if we translate all result to this particular setting, the corollary that we would be obtaining is that given a natural number L such that we have this inequality for L, so we have this lower bound for L, then this map is injective with probability 1. And we can derive another consequence that would follow from another result from the same paper, that essentially would say that if we have a translation invariant state psi now with periodic boundary conditions, then for a length that is also lower bounded by something that scales logarithmically with n, we know that psi is the unique ground state of a local Hamiltonian with probability 1. Okay, so these are the two main consequences that I wanted to mention of this result in the case of the matrix algebra. And now I'm going to proceed to the second part of the talk, where we will extend these things to Lie algebras. So if you want to ask any questions about the first part, I think it would be a good moment, because now there's going to be some change. Okay, so if there are no questions, we will just go to the second part of the talk. And the second part will be, the second paper that I mentioned, which is the one that is not on arXiv yet, and is how can you translate all these results to the Lie algebra setting? And you will see now why we are interested in this setting. It's not, we are interested in the mathematics per se, but we are more interested in the applications that this will have in different problems in quantum information, as I will mention later. So first of all, what we have to do is translate the notions that I was describing before to this Lie algebra case. And for that, we need to consider a Lie algebra, and we need to introduce the Lie length of a Lie generating system. So essentially now we consider a subset of the Lie algebra that is finite, and we define the Lie length of this Lie generating system U as the minimum L, as the minimum natural number L, such that the span of the UNs with n less than or equal to L coincides with the whole Lie algebra. And by this, the way to construct these UNs is the following. So first of all, we consider U. We define U1 as the span of U. Then we define U2 as the span of U with U1, the commutator of U with U1. And then we define U3 as the commutator of U with U2, and so on and so forth. So this is why we obtain, this is how we obtain UN. And now, in a more explicit form, we can see this construction as I write here. So this U to the kth power is just going to be essentially any element of the Lie algebra that can be written as the right nested commutators of k different elements in U. So it's going to be some construction like this. And in this particular case, we will be able to say that the Lie length of a Lie generating system is then given by the minimum natural number, such that our Lie algebra coincides with the span of the kth power of this U, of this generating system. Okay, so it's exactly the same definition that I had before for the words constructed from A and B. But now, first of all, U doesn't necessarily have two elements. In general, U has more elements. And secondly, the product that I'm taking here is not the product of matrices, but it's just the commutator of matrices. That's the only difference. And I'm mentioning this problem essentially because now, since we can take the UNs just as the right nested commutators, for example, of all the elements of U, then we can take it as a grading of the Lie algebra, and the basis elements can be restricted to just left nested or right nested brackets. And that means that we can use some standard algorithms to find a basis with minimal length. So this standard algorithm that we are going to use is something that is called the tree structure algorithm, or the Lie tree algorithm. And this algorithm consists on the following. So first of all, it takes two matrices, for example, A and B. Then at the next step, it considers the commutator between A and B. Then at the next step, it considers the commutators of A and B with all the elements of the previous step, and so on and so forth. And this is why at every step, the number of different elements that appear here, it's duplicating. So it's multiplied by 2. And what it does at each step is check each of these new elements. It studies if the new element that has just created is linearly dependent with the previous ones or not. If it's linearly dependent, then it throws it away. But if it's not linearly, if it's linearly independent, then it keeps it. And it repeats this argument with all the new right nested commutators until at some point there are enough basis elements. So it's already generating the whole Lie algebra, or until the length reaches the dimension of the Lie algebra, in which case you know that then you're not going to be able to generate the Lie algebra ever. Because in this particular case, this wouldn't be a generating system. So this is something that has been done and that has been used previously for some problems and computationally. And well, what we did here was to essentially study what happened for this Lie tree algorithm for certain random pairs in some very particular cases of Lie algebras, the most typical ones. So for example, we studied this in the case of SUN, and we studied well, this for n for dimension until 20. And what we did was to check when we were already reaching, at which length we were already reaching the whole generation of the Lie algebra. And we did some numerics, and we observed a graph like the one that I'm drawing here. And if you see, if you could write a curve that would adjust to these points more or less, it would be something logarithmic. So that means that we had some intuition that the Lie length of a Lie algebra like SUN should be something like logarithm of n with probability 1. So in this particular case, it would be theta of log of n almost surely. And we also observed that this happens for any other typical Lie algebra, like all these ones. So this is why here I'm just drawing this situation for SUN. And well, what I'm showing right now was just some numerics, but now what we have done in this last paper is to prove analytically all these results. So the way to show you how to translate the results from the matrix algebra case to the Lie algebra case is the following. If you remember, for the matrix algebra case, I was defining all the elements of all the words of length L. And I was talking about, well, I was asking what is the minimum length such that all these words of length exactly L span the whole matrix algebra. And then the conjecture was that L has to be taken of order n squared. And I wrote these two specific cases. So I said that the best bound to date is of order n squared log of n, and that there are some examples of order n squared. So now we can translate everything to the Lie algebra case. So now, as I said, we can write the products with commutators instead of the usual matrix products. We can ask the same question. So given a generating system U, what is the minimum length such that all words of length exactly that number span the whole Lie algebra, sorry. And what we have conjectured in this new paper is that for any finite generating system, we can have this quantity to be of order, this length to be of order dimension of the Lie algebra. And the best bound that can be proven, also completely translated from the matrix algebra case, is of order dimension of the Lie algebra, log of the dimension of the Lie algebra. So again, with a log overhead. But then, of course, we will have again the same question. We don't care about any finite generating system. We don't care about any finite generating system here as well. We only care about something that happens with probability 1. So what can we say with probability 1? And now with probability 1, we have a couple of interesting results from my point of view. The first one of them has to do with simple Lie algebras. So let me remind you that a simple Lie algebra is just a non-abelian Lie algebra that has non-zero proper ideals. So some examples are like the sets of, well, the special linear Lie algebra, which is just the set of n times n complex matrices with trace 0, and the special orthogonal Lie algebra, which is the set of n times n skew-symmetric matrices. And for these simple Lie algebras, what we can show is exactly the same as before. So we can show that again, if we have a Lie algebra G, and if we have a generating system, a generating set that has finite cardinality, then the Lie length is just of order theta log of the dimension of the Lie algebra. So it's exactly the same thing that we were obtaining for matrix algebras. And if instead of considering now simple Lie algebras, you consider semi-simple Lie algebras, you essentially obtain precisely the same. So a semi-simple Lie algebra is just a direct sum of simple Lie algebras. And what we are doing is now just translating all the results that we did for matrix algebras in the simple case to the semi-simple case at the level of the matrix algebra, so at the level of the associative algebra. And we also translated it from the matrix algebra case to the Lie algebra case. And this is how we could obtain this result, which essentially tells us the same thing. So the Lie algebra for a semi-simple the Lie length for a semi-simple Lie algebra is also of order theta of log of the dimension of the Lie algebra. And well, more specifically, if you want to see how this behaves, since your Lie algebra can be decomposed as a direct sum of smaller Lie algebras, of simple Lie algebras, then the order that you would obtain here is something of this form. So you would just take the log of the maximum of the dimensions of all the components here, and you will have to add it up to the cardinality of the different, well, of all the terms that you have in this decomposition. And this is how you will be able to compute this Lie length. Okay, so Until now, of course, I'm not giving any proof of this part because it's quite technical, but just the ideas, just to tell you what I want you to take from here is that all the results I mentioned before from matrix algebras can be translated to Lie algebras. And now you already have all these results for the semi-simple Lie algebra case, but there is a problem here. Someone might be complaining because, of course, I'm interested in all these results because they happen generically, so they happen with probability 1. But the problem is that when now you're studying a physically relevant system, usually you have some specific matrices that you need to work with. And these specific matrices sometimes are not generic. In the sense, for example, that if you consider a matrix that has like 1 and all the other entries are zeros, this is very much non-generic because this has a lot of eigenvalues that are 0. And this is not sampled with probability 1. This is never obtained there. That means, in particular, that if we want our results to be applicable to physically relevant systems, we have to change what we are doing here. And this is why the last result that I want to present today, I think is probably the most interesting one for applications. Because now you have, for example, the problem of generating unitaries, or the problem of Hamiltonian simulation, which is going to be for us something analogous. And in particular, we are going to consider some brick wall structure, like the one I am drawing here. So we have a circuit with 2 to the n qubits, and I consider the number of qubits here as a power of 2 because, well, for simplicity, essentially, because it's simpler for the proof, but this can be done with any number of qubits. And now you consider a lot of unitaries, a lot of 2 local gates on this circuit. And you also need to consider some 1 local gate. And what you are trying to do is generate a global unitary, any global unitary of dimension 2 to the 2 to the n times 2 to the 2 to the n with this brick wall structure. And the question is, if I'm given a finite set of unitaries in 2 gates, 2 local gates, in the form of 2 local gates and in the form of 1 local gate, how many layers for this circuit would I need in order to be able to generate any unitary of this dimension? And well, of course, if you consider just these layers that I'm drawing here, this is very much non-generic, because if you see this unitary that would be taken as the tensor product of these 4 unitaries, this is not generic. This is something that you wouldn't obtain with this probability 1 sampling that I was mentioning before. So what we have to do in this particular case is go to a subalgebra that lives, for example, now only in these 2 qubits, in the space generated by these 2 qubits. And then we have to check whether we have a generating system there that is generic, because it might be the case that is generic in this subalgebra. And when this is the case, and you have it for all the combination of qubits that you can write here, then that means that even though your unitaries are not generic in the global algebra, they are generic in the little subalgebras, and then you can sort of glue what happens there. So you reduce to these subalgebras, you do your generation there using the previous theorems that I mentioned before. And once you have these generations, you glue all of them together, and then you are able to generate the global Lie algebra. Okay, so this is what we do here. And in particular, the result we would obtain in this specific case would be the following. So you consider the 2 to the n qubits, as I was drawing here, and now you consider this set of 2 local generators. So first of all, you consider the products of 2 Pauli matrices in 2 consecutive qubits, that is sigma x in these 2 consecutive qubits, and the same thing with sigma z, but only considering the collection of all these possible 2 local generators wouldn't be enough to be able to generate the whole Lie algebra. You additionally have to also consider all the sigma x and all the sigma z's in all the possible qubits. And if you consider this as your U, as your generating system, then you know that taking enough products of these elements, you would be able to generate the whole Lie algebra. So you would essentially be able to generate any unitary here. And what you know is that the depth that you will have to take here would be something of order 2 to the n squared. And maybe this right now doesn't tell you a lot about the length or about how efficient this would be. But what I can tell you is that the efficiency in this particular case is going to be much worse than in the generic case. And that's pretty obvious, actually, because if you consider a matrix that has a 1 and a lot of zeros, for example, which is how this could be, and then you start to multiply it with all other different matrices in order to be able to generate a bigger algebra, then you see that with any possible product, you would increase the dimension very little. So this is why the efficiency when constructing the whole Lie algebra would be very bad using this construction. However, in particular, we know that even though it's pretty bad, it's much better than just brute force. So it's much better than just using all the possible layers that reach until the dimension of the Hilbert space to just construct the whole Lie algebra. Because what you can see is that there should be a minus here. What you can see is that, O to the 2 to the n squared is 2 to the log of the dimension of the Hilbert space that is underlying in this construction to the square power, and therefore this is much smaller than the dimension of the Hilbert space, as I said. So even though this is probably not optimal, it's also much better than just the brute force argument. And let me just mention 2 applications of this result, although I think the main application is what I mentioned here. It's just for unitary generation or for Hamiltonian simulation, which is essentially the same. But 2 further consequences that I wanted to mention have to do with the Lie-Trotter formula or with the Baker-Campbell-Hausdorff formula, because essentially they are very much related for this context. And for the Lie-Trotter formula, what we do is take the sum between A and B, and we take a parameter t larger than or equal to 0. And then we know that the Lie-Trotter formula provides an expression for the exponential of the sum of A and B with this parameter t. And it's given by this expression here. So what we want to do essentially, what you have to take into account here is that if you consider the exponential of the sum of 2 scalars, this exponential, of course, we know that we can write it as the product of the exponentials of each of these scalars. And of course, for matrices in general, we cannot do that. But this is the most accurate way, probably, to write something similar. So we cannot write in general that this is equals to just e to the ta, e to the tb, but we can write it as the limit with n tending to infinity of the nth power of these products. And this formula is frequently used in many different contexts in quantum information theory. But in particular, I want to study here the relation that it has to the Baker-Campbell-Hausdorff formula. And the Baker-Campbell-Hausdorff formula is essentially the solution for Z to the equation that I'm writing here. So it's the same thing that I was saying before. If now you take e to the x times e to the y, how can you write Z such that you have an equality here? And well, this formula has also been explored quite a lot in the last few years. And there is quite some knowledge, but it's not completely well understood. And what we can write, for example, for the first terms of the VCH is some expression like the one I'm drawing here. So we can write this set as x plus y plus 1/2 of the commutator plus these commutators with 3 elements minus this commutator with 4 elements, and so on and so forth. So we can write this infinite collection of right-nested commutators with x and y. And then essentially what our result would say in this context is that since you want to generate any possible set, we don't know how to compute the coefficients that will appear in this expression, but what we know is that it would be enough to generate only these commutators until length of order log of n. Because from there on, for us, any other commutator could just be generated with as a combination of the previous ones. So this is what we have been proving before. So this would be one consequence in terms of the Lie-Trotter formula or the Baker-Campbell-Hausdorff formula. And another consequence we could mention has to do with overparametrization of quantum neural networks, which is surprising because in principle it seems that it doesn't have anything to do, but actually the construction is essentially the same that we were mentioning before. So now what we are going to do here is consider a quantum neural network that is parameterized as a quantum circuit, U of theta. So we can just write this u of theta as a product of different layers of ul of theta L, and each of them is going to be written also as a product of different unitaries that are going to be like the two local generators that I was mentioning before. So in this particular formulation, this H sub k, the collection of the H sub k is going to be our generating system. And then one can consider the dynamical Lie algebra that is generated by this generating system S as just the span of now not the H case, but the H case multiplied by I. And now if we take this span of the nth power of these elements and we take n to be as large as possible, this is how we generate this Lie algebra. And I'm just mentioning this here because this dynamical Lie algebra has been explored very frequently in projects related with overparametrization of quantum neural networks. And the first thing that is mentioned is that it is obtained from the BCH formula. And that means essentially that what I was mentioning before is also applicable here. And apart from that, in this particular paper of Laroca et al., for example, from 2 years ago, what they show is that the quantum neural network is overparametrized above a critical number that is related to the dimension of this dynamical Lie algebra. So that means essentially that our result could be interpreted here as the efficiency of computation of this dynamical Lie algebra, because it would mean that we know how many products we have to take here so that we have already generated the whole Lie algebra. So where we can truncate this n. And without going into any further consequences, what I'm going to do is just conclude, recalling the things that I've been discussing before. So first of all, for matrix algebras, we have explored two different problems. We have explored what is the minimum number such that all words of length at most that number span the whole matrix algebra. And we've seen that the conjecture is order of O of n, but the best bound is O of n log of n, so a log of n overhead. And when we consider the words of exactly a specific natural number, we have the analogous problem. The conjecture is of order n squared, but the best bound also has a log of n overhead. And what we have proven in this particular case is that both lengths here can be taken to be of order log of n, so much smaller than this n log of n and this n squared log of n. And we have seen applications of this result in the context of primitive quantum channels and in the context of matrix product states for injectivity of MPS. And now for the Lie algebra case, we have considered the analogous problem to the second one here. So when we consider now, instead of products of matrices, just the commutators of matrices, what is the minimum natural number such that all the words on a generating system of exactly that natural number span the whole Lie algebra? And what we have seen is that we can conjecture in general, that this order is this order is of the dimension of the Lie algebra. But what we have proven is that the best bound today is the dimension of the Lie algebra log of the dimension of the Lie algebra. So again, a log of the dimension overhead. And what we have also proven is that with probability 1, the Lie length, so this L here, can be taken to be of just order of log of the dimension of the Lie algebra for the simple case. And in the most interesting problem, I would say, for the non-generic local case, even though it's much less efficient, we can say quite much more than in the case of just computing everything by brute force. And we've seen how to apply that for Hamiltonian simulation, for example. So this is everything I wanted to tell you about today. So thank you very much for your attention. And of course, I would be very happy to take any of your questions.
Thank you, Angela, for the talk. So now we open again for questions. Is there any questions? Anyone in YouTube can also put questions there, and I'm checking here the questions. I can bring it here to Zoom. Just okay, let's see. I mean, I'm just curious. So you are I mean, are you working already or trying to do applications for Hamiltonian simulations and compare with other ways to make this, I mean, methods for these simulations? I mean,
So we are trying to combine them with some other methods, because here you can show efficiency once you know that you have a generating system. And there are some people working on the question when they have a generating system. So what we're essentially doing is combine both methods to say, okay, with the things you do, you have a generating system, and with the things we do, we have efficiency in the generation. Something like that. But of course, I have to admit here that this is a theoretical result, in the sense that we say with probability 1 this happens, but this is not constructive, which means that even if you know that you can always generate only taking products of a certain length, this doesn't tell you what are the coefficients that you need for the generation. So I agree that we are still a bit far from super useful applications in some sense.
there is no clear way to construct all the.
No, this is we keep getting the same question, like how do you make this constructive? Like if you say you have with probability 1 this set of words that does whatever, how do you construct this set of words? And it's true that there's no clear way to do that, because this is just a theoretical result. So I would say that this is a line to explore in the future.
Okay. Okay. Any other questions in YouTube? Okay, so I'd like to really thank you again, Angela, for taking the time to show and talk. I mean, the results in the talk, and I mean, no more. I don't think there is any other questions. So thank you, Angela, and everyone that is watching here in YouTube. And I mean, we'll be back in 15 days, and hope to see you again, Angela. Thank you.
Thank you very much for the invitation.
Oh, it's a pleasure.
Okay, thank you very much. Then have a nice day.
You too.
Bye.
Bye, bye. Beleza, Ananda? Eu vou ter que sair correndo aqui também, que eu tenho um outro seminário agora. Obrigado aí pela organização.
Maravilha, professor.